Well, welcome back. We are continuing our discussion about related rates. Last week we looked at things in motion that involve changes in area, changes in volume. So this week we're going to talk about changes that are going to be affecting lengths or distances on objects. But again, the presumption is that change only happens as time has gone by. So all of these rates are changing with respect to time. These questions will start looking familiar. You'll think you've seen them before, and we did. We saw them in our optimization section of this chapter where you had to set up a very similar diagram. You had to decide on your variables, but the questions you were being asked were related to optimization. Optimization is getting the best scenario for what you're looking for. So maybe optimizing surface area would mean figuring out the values that will produce the smallest surface area. Or maybe we're trying to optimize volume, so therefore figuring out the dimensions that will give the largest possible volume. Those things were not given a time frame. So they didn't tell you how something was growing or reducing in a certain time. So they were not related rates questions. In related rates questions, they will have to give you a rate. So literally you will see meters per second or feet per hour or something like that, okay? So not trying to find values of distance and time, trying to find rates typically. So watch for that word rate. What is your plan going to be? Diagrams are very, very useful. Then you decide what equation that you're going to be dealing with, and if something is fixed, so something never undergoes change, then it needs to go into that original formula right away. You differentiate with respect to time, which means you are putting in d something over dt following every single variable that you had in the equation. So you may have more than one variable. We typically like to get ourselves down to one variable, but if you were given rates that correspond to every variable you were given, you're actually safe. It would be okay to keep all your different variables. And it's going to be very important now, since we're talking rates, we're going to get into a discussion of velocity, and it's important that you're including signs. And it is not a matter of, oh, something's in motion downward, I'm going to call that velocity negative. It is no longer that simple. The diagram will help you decide on whether your velocity should be positive or negative. If that motion is increasing a length, then that velocity is positive. If the motion is decreasing a length, then that velocity, not sure what I said there. If the velocity is increasing a length, then your velocity is positive. If your velocity is decreasing a length, then your velocity would be negative. Not it's going up, so it's positive, down, so it's negative. Okay, and then you solve for whatever you're being asked to solve for. Units, you must include units with your answers, and you must answer in a complete sentence. I won't take the time to write down sentences, but for you to make sure you're getting your maximum amount of marks, you definitely want to have a sentence with your final answer. And watch out how you're saying things. Don't say the rate was decreasing by a rate of -2 meters per second. You have a double negative. When you say decrease and then you say negative, you're actually turning that around, and you would be saying something is increasing. So watch the terminology. So 4 examples today. So the first scenario we've kind of seen before. We have 2 boats. Or we had 2 planes, we had 2 people walking, whatever. You knew you would always have them starting at some point on the X and Y axis. This scenario is going to be 2 boats are right here at this port. And they're going to leave the port at the same time. One's going to be going south, and it's going to be going 40 kilometers per hour. And another one's going to be heading west, and it's going 30 kilometers per hour. Now, an optimization question would say, when are they going to be closest? Right then. They're never going to be closer than right when they're docked next to each other. So you're not going to have that question, and you're not going to have, when are they farthest apart? Well, I guess it depends on that body of water, how far apart they could ever be. That's not the question. The question is, as time, this picture is only what it is for a split second. They're both going to start to move. And as they're going to start to move, they are actually creating a triangle. So their motion is creating a triangle. So with time, a triangle is being formed. So what happens? Well, maybe a few minutes later, this guy's here and this guy's here. So now we have this triangle. And a little bit later, this one's here and this one's here. And now we have this triangle. So this is going to be the shape where you are going to have to now talk about the relationship between all of these quantities. So think about these velocities. It might be tempted to say this 40 kilometers an hour is negative because it's heading down. This 30 kilometers an hour maybe was negative because it's heading left. But no, look at the effect. Look at the green triangle we had here. And what was the effect of this motion? This 40, as time went by, was making this side of the triangle longer. So this rate is positive. This 30, as time went by and you kept going 30 kilometers an hour, it was increasing this side. So this would be positive. So what variables are we going to use? You know what? This is a horizontal motion. So this has to do with x. So this is the horizontal rate. That would be how things are moving on the x-axis according to time. So this 30 is dx over dt. This is a vertical motion, so this would be my dy over dt. The distance between them is always going to be d. So if I'm looking at this scenario and they will have to give me a time frame because they're not always, the rate between them was increasing for sure. Here it was increasing, but the rate at this point might have been increasing faster than the rate was increasing in the distance between them then. So they would give you a time frame. So I'm going to say 3 hours later, okay, how fast is that line growing? So here's why we're calling it lengths or distances. Well, I need a formula. How am I going to come up with the formula? Ultimately, what I'm looking at is an x value, a y value, and a d value. So my basic formula is x squared plus y squared equals d squared. Will any of these sides remain fixed and never change? Nope, they're always changing. So I can go ahead and differentiate. If something about this, like if this was never moving, then I would actually put in that value here and work it out. But everything is in motion. So now you differentiate. So you'll have 2x dx over dt plus 2y dy over dt equals 2d dd over dt. To save yourself some work, all of those 2's can be divided out from the equation. So now what do we know? We know the horizontal rate, we know the vertical rate. This is what we're supposed to be finding. How fast is that distance between them changing? So I need to come up with an x value at that moment in time, a y value, and a d value. Well, at what time is that? 3 hours later. So if these have been in motion, this was going 30 kilometers an hour for 3 hours. This has now gone 90. Here, this one was going 40 kilometers an hour for 3 hours. So this one has gone 120. So here is now my right triangle. I would do Pythagorean theorem and get this value. If it's not nice, leave it under a radical sign. But this turns out to be nice. So I do my 90 squared plus 120 squared equals d squared, and I solve. D is 150. So you have everything you need to go and substitute in here. So my x value is 90. The horizontal rate was positive 30. You might want to put a positive in there. My y value was positive 120. Distances are positive. The y rate was positive 40. Then there's a 2, and my d value was, the 2 is not there. My d value is 150, and I'm solving for dd over dt. So putting all these together, I believe, what do I get here? I think it's 7,500, yep. And then 150 dd over dt. And once I solve, I will have dd over dt is positive 50. This needs units. What was distance being measured in? Kilometers. What was time being measured in? Hours. So the distance in between them was increasing. This would be my sentence. How was the distance between them changing 3 hours later? I would use the word increasing. I would say the distance between them is increasing at a rate of 50 kilometers per hour. Okay. So that would be a very basic question on one of these two things in motion on a grid. Okay, we can change this just a little bit. So question number 2, still we're going to have, let's see, these are 2 people in motion here, and I've got the scenario at a certain time. Let's say this is 9 a.m. and I'll have two people, A and B. A is 80 kilometers west of B. Okay, so they're in a horizontal line from each other. So they're either here and here or here and here. They tell you A is going east. So A is going this way, that's going to work. B is going south. So if I had A and B, could B go south if this was my setup? Yes, it could. If I had A and B here, can B go south? No, it can't. It's into this void. So nice setup here. Here are my two objects, and this is 80 west, but we're only at that split second in time. A is traveling east at 15 kilometers an hour, and B is going to be going south at 10 kilometers an hour. At 11 a.m., find the rate of change of the distance between them. So, okay, I have a different picture then. So 2 hours later, what has gone on? Oops, that didn't draw. Okay, so A was here and B was here, and this was 80. So at 11 a.m., 2 hours has gone by. A is going 15 kilometers an hour. So A has gone 30 kilometers, right? So A has gone 30. So here's now where A is sitting. What is this distance? This must be 50 because that total distance was 80. So the 50 is now important. And B was tootling on at 10 kilometers an hour for 2 hours, so it's gone 20. I'm not drawing these in proportion. So this is now 20. So there's A, here's B, that's where they're at now, so here's my triangle. I don't know D. I would use Pythagorean theorem to find that distance D, and it's going to end up being root 2900. So you could simplify this. Let's see, if we simplified it, it would be 10 root 29. There's not really much purpose in doing this. Okay, so let's say we're going to be fine leaving things not reduced into mixed radicals. So now what? Was there anything about this situation that never changed? No, everything was always changing. So we have x squared plus y squared is d squared. We will get our typical formula for this motion question. Everything is being differentiated with respect to time. We will get rid of the 2's, and we will think about everything that we know. So we have our x value, our y value, and our d value. So we have x, y, and d. Yep, I have forgotten. There we go. D, lots of d's there. So I have these three values now. Do I have the rate of how this was moving? Yes, it was. 15 kilometers per hour. Now, is that 15 a positive 15 or a negative 15? As this A person was in motion, was it, as it kept going in motion, was this side of the triangle increasing or decreasing? It's decreasing, right? A few seconds later, here's the triangle. So this is negative. So this dx over dt is negative 15 because of its effect on the drawing. So the distance on x was 50. Then I go plus. Now how about my y value? My y value was 20. And how about this motion? This 10 kilometers per hour south. As that motion is taking place, that side of the triangle is getting longer. So this is a positive 10 kilometers per hour. And that's going to equal the d value, which was root 2900. And then we have dd over dt. So adding everything here together and dividing and without any reducing, I will have negative 550 over root 2900. That's my dd over dt. And I need units. So d was in distance, this is kilometers. T was in time, so this is hours. So the distance between them was decreasing at this rate. You could, I mean, this is an exact value. If you want to round it to a decimal value, you would have that. But the idea of the distance, how is that distance between them changing? It's decreasing. So that means they're not as close as they will ever be. Because what should the rate between them be? How should that distance be changing between them when they're as close as they will ever be? That rate should be 0. because you're getting closer and closer. So the way that distance is changing, getting closer and closer, right? Until the rate between them is not changing, and then that rate between them as they're passing, and there's more and more distance between them as time goes by, the rate would be increasing. So there's an interesting understanding of when this rate is decreasing, that's actually telling me they're not as close as they ever could be. And then someone comes along and say, okay, how close could they ever be? Well, that was the optimization question, right? The optimization question would never have given you, oh, at 11. That's what you would have been asked to find. You would have said, when are they closest ever? So what would your drawing be? Just to talk about this is good review. So here was the first scenario. All you knew here, this was our 80. And they were going 15 kilometers per hour. So what happened as time went by, we have this scenario. So we don't know how long this took. This question, we knew that took 2 hours, so we could say they went 30. But we don't know how much time that takes. So remember, we called that distance 15t. So what was left here? 80 minus 15t. That represented that side of the triangle. This was going 10 kilometers an hour, but I don't know for how many hours. So here was the setup before, if this could be an optimization question. So now it would be d squared equals 10t squared plus 80 minus 15t squared. We're going to differentiate, right? 2d prime plus 2, equals 2 10t, followed by the chain rule, and etc. And you would divide everything by 2 and just solve for making the top equal to 0. And you would be solving for a time. And you say, oh, 5 minutes. So your answer would be, oh, 5 minutes after they had started, they would be as close as they're ever going to be. So really read the question carefully and make sure you know what you're being asked. Okay? So optimization will not have a rate in there and ask you how something is changing at a certain time. So those are 2 motion problems. The other 2 that we see a lot of is the ladder question. And what do ladders typically do? They can fall. Here, I'm just going to adjust this here. So a very, very common question in this unit is addressing what happens as you have a ladder propped up. Okay, so it's on the ground and it's propped against a house. Okay, and we're going to presume that building is vertical to the ground. And the question is going to be, how fast is this ladder falling? But it might say, how fast is the top of the ladder falling? Or how fast is the bottom of the ladder sliding away from the wall? You say, well, aren't they the same? Well, we'll wait and see. We will see if they're the same. Okay, so information you would be given. Okay, the ladder is 8 meters long. And originally, let's see here, the bottom of the ladder is 400 centimeters away from the wall. And the top, this is important, the top of the ladder starts falling. No, that's what we're going to be asked to find. So how fast is the top of the ladder falling? If we were going to be doing a trig unit, we could be asked, how fast is this angle increasing when the ladder's falling? Or how fast is this angle decreasing as the ladder's falling? So all sorts of things. But again, we weren't going to be doing our trig unit. Okay, but they do tell you that the bottom of the ladder is going to be sliding out from the wall at a rate of 0.8 meters per second. So this is everything that you've been given, and now you have to solve for how fast is the top of the ladder falling. So we have a y value, we have an x value, and you have to decide, and an 8 value. So out of those 3 values, is anything fixed, right? Because this is another triangle. So we're going to come up with our formula for what we see here. Well, it's x squared plus y squared would be d squared, right? That distance or length. But this is fixed, right? That is fixed. So it has to go in. So something that is fixed goes in right away. Doesn't matter how low or how high that ladder is, it's 8 meters. So now we're going to differentiate. 2x dx over dt plus 2y dy over dt And what's the derivative of a constant? 0. So that is actually less work. I can still divide by my 2's. So I know still there are 4 unknowns here, right? The horizontal length that I'm talking about, the vertical length I'm talking about, how fast the bottom of the ladder is sliding, and how fast the top of the ladder is sliding. So do notice little things, meters and centimeters. So they would not be, you would need to get everything into the same units. So 400 centimeters is just 4 meters. And actually that wasn't given to me, that wouldn't have been given to me right off the bat. That was, I think, the when situation. So I was just given that situation right there to start. Okay, and then the question is, how fast is the top of the ladder falling when the bottom is that 4 meters from the wall? Okay, so there's that when, and we've seen before that word when is not fixed. That's something in motion. So I need a formula talking about motion before I could ever put that 4 in here. So the 4 was not fixed, right? The 8 is. So if I start thinking about that, all right, so the ladder had been falling. Everything stops when the bottom of the ladder is 4 meters away from the wall. This is an 8, and then I guess I need to do Pythagorean theorem to find out what this would be at that moment in time. That ends up being 64 minus root of 48, I believe. So y after Pythagorean theorem is root 48. So filling everything in. What's my x value? 4. So this dx over dt that they told me was 0.8. The motion is that way. Would you say that this dx over dt is positive or negative? It's positive because this side is growing as this ladder is falling down, right? Here would be the scenario constantly. So this side grows as this side falls. So this is positive 0.8. When we do find this dy over dt, it's going to be a negative rate because with its motion, that side of the triangle was decreasing. So I'm going to have 4, 0.8 plus y, which is root 48, dy over dt equals 0. Moving that over to the side would be negative. So I'm going to have this negative 3.2, and then I'm going to divide by root 48. So this would have units. This was all being measured in meters per second. So again, watch your wording. You would say the top, okay, and just so you know, I'm changing this to a decimal, was 0.462 meters per second. So the sentence would be, the top of the ladder is falling at a rate of positive 3.2 divided by 48 meters per second, right? Don't say a double negative. Look at that rate. It's falling at this rate, but it was, so it's falling slower. So yes, it's falling slower than the bottom of the ladder was moving out. The bottom of the ladder was moving out at 0.8 meters per second, and the top is falling down at only 0.4-ish meters per second. So there is a difference in how fast the top versus the bottom is moving. Ha! But don't try this on your own. Don't try this. Don't be the person up here and somebody's got a radar gun on you testing how fast you're falling. Okay, last question here. Another one that we see very often in this unit is about shadows and understanding how shadows work. So first of all, shadows exist really on the ground, unless let's say you're shining a flashlight at a wall. But when we're talking about a light source at night, a street light, and you are right smack under that street light. Okay, so here's some kind of street light shining. And if you were standing right here, your shadow would be very tiny, right? But you start walking, and let's say when you're over here, your shadow started appearing here. And actually, the farther away you get, that shadow, you can't even see the head of the shadow anymore. It has definitely increased as you walked away. So from nothing to something increasing. So we draw this picture. So here's some person, and where would the shadow be? Remember, shadows are on the ground. So I'm just going to create a triangle situation here. Okay, so this, anytime you're dealing with a triangle situation, this is how you want to approach it. The person could be walking away from the light source, but this is the shadow. For sure, right here, that is the shadow on the ground. And it is changing. That entire length is growing the farther away you go, shrinking the farther away you came back. So you'll be given some information. Let's say this street light is 10 feet tall. This person is 6 feet tall. We'll say they're walking away. Okay, so this is not a shadow. This is the distance. And they're walking away from this light source at a rate. So this is horizontal. So I'm going to call it dx over dt at a rate of 4 feet per second. Now, you tell me, is that going to be positive or negative? Is that increasing something or decreasing something? You'll see in a minute, it's a decrease situation. So, not because I'm heading right, just because of the effect on that shadow. So we want to deal with triangles. This particular side of the triangle was always very important in the other questions that we did. Now it isn't. This has nothing to do with the shadow. It has nothing to do with the height of the person. So the hypotenuse doesn't really play a role. What I would much rather do is consider the heights and the distances. So instead of saying, I have a big triangle and I have a little triangle, this is how we want you to split up your work. Okay, the two triangles that become paramount to all your work are these two right here. Okay, they are similar triangles. They both, which means their angles are the same. This is 90, this is 90. This corner and this corner would have the same angle, and these top corners would have the same angles. They're not the same size. One of these, and my drawing is not even drawn to scale, one of these triangles is definitely bigger than the other, but they're similar triangles. So with similar triangles, you can set up proportions, just like we did in any of those cone questions, where H to R always maintained a certain relationship. So what are my two triangles actually? If I just draw them separately and put on all my scales, or all my numbers, this triangle, this distance would be 6. This is my shadow, so I will call it S. This distance, if this was from here to here, the 6, this must have been 4. So this one is 4, and this is my horizontal distance, so this is an X. So really, I have that information, and then I know how this side of this triangle is growing the more this person walks. So dx over dt is positive 4 feet per second. I'm supposed to figure out as time goes by, how is this changing? So ds over dt, that's what I'm being asked to find. Okay, so we're almost there. So what is the proportion? Set it up however you want. You could say 4 to x. So I could say 4 to x is 6 to s. Or I could say 4 matches 6 as x matches s. However you do this, you're going to end up with the same formulas. Cross multiplying, here is going to give you 6x equals 4s. Here, 6x equals 4s. So it doesn't matter. So we have 6x equals 4s. That's your equation. That's how everything here is related to each other. Is anything fixed? That guy's height is fixed, but that's not what this is asking me for. X represents this distance, and it is not fixed. S represents this distance, and that is not fixed. So nothing's fixed here. So you differentiate. The derivative of this side is 6. Derivative of x with respect to time is dx over dt. 4 is 4. 4 is the derivative of this side. Derivative of s is ds over dt. What do I know here? I know the dx over dt. This becomes a 4. So ultimately this says 24 divided by 4, so my answer is 6, and that is my ds over dt. What are my units? This was all in feet, because the shadow is measured in feet, the time component is seconds. So this is saying that it actually didn't matter how far away you were from the light. There was no place to insert a certain value for that x. It didn't matter. So forever this shadow is increasing. The length of the shadow, this entire length, is forever increasing every second at a rate of 6 feet per second. And the last question that is quite often tacked on the end of this is now saying, okay, here's you, here's that person, and here's the tip. They're like taking a little laser pointer, and they're pointing the laser right here at the tip of their shadow. So yes, here's their shadow. It's looking kind of long. But they're trying to track the speed of the tip of the shadow, not how the shadow is growing, the tip. So if you had one of these lasers, and as you were walking, and the laser had a velocity counter on it, and you could just keep that laser as you're walking on that tip of that shadow and record the velocity, I guess speed too, of that tip. How fast is it going? The tip of the shadow's length is growing by 6 feet per second. How would you get how fast that just this very tip is moving? It is ridiculously easy. It's the idea of this is being pushed by two velocities. So the tip is simply moving at a sum of this velocity plus this velocity. This one we were given at 6 feet per second. This one we this was the 4. Okay, this one we just calculated as 6 feet per second. So if you ever get one of those questions, how is the tip of the shadow moving? You add. So the tip itself, that dot, how fast is that dot moving? You would say 10 feet per second. This line was increasing longer and longer by 6 feet per second, but the motion of the dot, or the tip of the shadow, was moving at 10 feet per second. That's it for our study. That's it for our applications of the derivatives. All of your optimization questions, which were what you covered up to the quiz, plus these last 2 weeks. So exam is next week. You should go back. There's only 4 examples here. See if you could do them on your own. We've picked certain ones out of the textbook. You have that review from last week, which we only assigned some area and volume questions. So now we're assigning on that last week's worksheet some related rates, distance and length problems, and then we're putting on a big review. A lot of those review questions we wrote omit, but definitely now it's time for you to summarize all your learning. So you really should just have to be learning from where you had the quiz. So reviewing this related rates, practicing the stuff when it's all thrown together, and being ready for your exam next week. Good luck with everything. Make sure you keep asking questions of your teachers and staying on track. Thanks for listening.